So today we are discussing the very fundamental model of the hydrogen atom, and we call it as a Bohr's atomic model. So today we are discussing Bohr's atomic model for hydrogen atom. So you know that hydrogen atom is the simplest atom which has a central part nucleus which has only one proton in the nucleus, and electron is revolving around the nucleus in the fixed orbit, and the distance between them is r. So now in this stage you are very much familiar about the quantum states. Before this, there was a theory that the electron is continuously rotating around the nucleus and radiating the energy. As long as it radiates the energy, its energy decreases and finally drops into the nucleus. So there is no any discrete energy levels. This was the previous concept which is now rejected. According to the Bohr's atomic model, the electron revolves in a certain quantum states. So Bohr gives the concept of the energy states. The electron remains in the energy state. So these energy states are quantized. These are the energy states which are the quantized. This is, let's say, first energy state, n is equal to 1, this is n is equal to 2, this is n is equal to 3, this is n is equal to 4, and this we call it as a K shell, L shell, M shell, N shell. So these are the energy states now. The electron remains in the energy state. Electron cannot remain in between these two states. And this energy state is a discrete energy states. These energy states are not continuous like that. Okay, as long as electron revolves, it radiates energy. Finally, the energy of the electron decreases and drops into the nucleus, and the atom collapses. So this is totally, absolutely the wrong, rejected theory. So now we believe the theory that as long as the electron revolves, it does not radiate the energy. It will only radiate the energy when electron de-excite from higher level to the lower level. So when de-excite from higher level to the lower level, it will radiate energy in the form of the photon, in the form of the packet of energy, in the form of the packets of energy. So here, when electron de-excite from one higher level to the lower level, it radiates the energy in the form of photon, HF. So here, this HF, which is the energy of the photon, is the energy difference of the two states, which is the final energy states minus initial energy state. Here, if we say that this is the final where the electron jumps, and this is the initial where the electron is there. So the difference of the energy states gives the energy of the photon. So from this relation, h is the Planck's constant, and f is the frequency of the photon, and ef is the final energy or energy of the state, energy of the level where the electron jumps, and ei is the initial energy from where the electron jumps. So the energy of the photon is equal to the energy difference of the two states. This equation can be rewritten in the form of the wavelength. This is equation number 1. This is known as the first postulate. As long as the electron revolves, it does not radiate the energy. It will only radiate the energy when it de-excites from higher level to the lower level. The second is that the angular momentum is quantized. It means the electron will remain in the quantum state. So the angular momentum is quantized. It means angular momentum L is equal to n h cut, or mvr, which is the angular momentum, is equal to nh cut, or nh cut is equal to h upon 2 pi. We may call this is equation number 2. It means this states that the electron will only remain in a certain quantum state. Electron cannot remain in between two states. So here the electron may be either in this state, electron may be either in this state, electron may be either in this state. It will always remain in a state. So this is the second postulate. Or sometimes we may call this is the first postulate and this is the second postulate. So from these two postulates, the electron is revolving. When the electron is revolving, you know that the motion is a circular motion. And when a particle is moving in a circular motion, there is a force which we call it as a centripetal force. So in this particular case, there are two forces. One is the force between electron and proton, which is the force due to their charged nature, and that force is known as a Coulomb force. And the direction of the Coulomb force is always from positive to the negative. This is known as a conventional direction. It means the direction of the force is always from positive charge to the negative charge. So here, and the direction of the centripetal force is always towards the center. So here, in this particular case, both forces are balanced. If we look here, the centripetal force whose direction is downward, Fc, which we call it as a centripetal force, and the Coulomb force whose direction is from positive to negative, whose direction is upward here, or whose direction is upward here. So these both forces are balanced with each other. As a resultant, the electron will remain in a stable orbit. If any force whose magnitude is large, the electron will move towards that force. So as a resultant, the centripetal force is balanced by the force is balanced by the Coulomb force. As a resultant, the electron revolves in orbit. As a resultant, electron revolve in orbit. So the centripetal force Fc, which is equal to mv square over r, this is called the centripetal force, and the centripetal force is balanced by the Coulomb force, which is equal to 1 upon 4 pi epsilon naught. This is Coulomb force E square upon r square. For hydrogen atom, Z is equal to 1 4, so we have written directly E square upon r square. So this is known as a centripetal force. So now here in this case, this is, let's say, equation number 3. This is equation number 3. So now we have 3 equations. This is equation number 1, which is gives the energy of photon is equal to energy difference of two states. This is equation number 2. Angular momentum is quantized. This is equation number 3. From these 3 equations, we have seen that the radius of the nth orbit is equal to, or from these equations, we have seen that the radius of the nth orbit is Rn is equal to the epsilon naught h square over pi me square into n square. It means the radius is depending some constant value. This is constant value. Epsilon naught is the permittivity of the free space, which is constant. H square is the Planck's constant here. H square is also the Planck's constant, and pi is also constant. M is the mass of the electron and E is the charge of the electron. These all things are constant into n square. This indicates that the radius of each orbit, nth orbit, it means this is n is equal to 1, this is n is equal to 2, this is n is equal to 3, n is equal to 4. It means if we substitute the value of n is equal to 1, it will give you the radius of the first orbit. If you substitute the value of n is equal to 2, it will give you the radius of the second orbit. If you substitute n is equal to 3, it will give you the radius of third orbit. And this term, which is the constant term, this is known as A naught into n square. A naught is known as Bohr's first radius. So for n1, R1 is equal to A naught. Because n is equal to 1, we call it as this. For R2, radius of the second orbit is equal to A naught into 2 pi square 4. So square of 2 is equal to 4. R2 is equal to 4 A naught. So R1 is equal to A naught. So this is the way to calculate the radius. So now how to calculate the energy? The energy can be calculated as, if we look here, the energy or En, energy of the electron in the nth orbit is equal to minus n e raised to power 4 divided by 8 epsilon naught square h square into 1 upon n square. This is the energy of the electron in the nth orbit. It means the energy of electron in each orbit is depending by 1 upon r square. This is the constant term. If we look at n is the mass of electron, constant. E is the charge of electron, which is also constant. 8 epsilon naught h square, this whole term is also constant. So we may call it as a En is equal to minus E naught, which is equal to this constant divided by n square. And this E naught is known as minus 13.6 electron volt upon n square. So here for n is equal to 1, E1 is equal to minus 13.6 electron volt. E2, energy of the second orbital is equal to minus n is equal to 4, 13.6 divided by 4 is equal to 3.5. 3.4. This is 3.4 electron volt. So here, if we look here, this is the energy of the first orbit and energy of the second orbit. Here, if we look here, this is the nucleus, this is first orbit, this is second orbit. N is equal to 1, N is equal to 2. So here the electron jumps from 2 to 1. The binding energy of electron here is 13.6 electron volt. Binding energy is equal to here is equal to 3.4 electron volt. So here the difference of these two is equal to 10.2 electron volt. So it means if the electron jumps from higher level to the lower level, it emits out the photon. When the electron de-excite from higher level n is equal to 2 to the lower level n is equal to 1, as a resultant it emit out the photon, emit out the packet of energy whose energy is h nu, yeah, hf is equal to energy difference of two states E2 minus E1, yeah, E1 minus E2, EF minus EI, final minus initial, and final is equal to minus 13.6 minus minus plus 3.4, this is equal to 10.2. So negative sign is only indicates the binding energy. So the energy of the emitted photon is equal to 10.2 electron volt. It means when the electron jumps from n is equal to 2 to n is equal to 1, as a resultant it emits out the photon whose energy is equal to this. This is the energy. And if you calculate the wavelength from this equation, wavelength is equal to hc over lambda, because f is equal to c over lambda, and this is equal to 10.2 electron volt. From this relation, you can easily find out the wavelength. Okay, what is the wavelength of the emitted photon? Similarly, here this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and so on. It means the deficiency is here, the electron jumps over here, this emit out the photon. The electron may be de-excite from this level to this level, and this gives you the series from this level to this level, from n is equal to 4 to n is equal to 1. So this gives you the series which we call it as a Lyman series, in which the final NF is equal to 1 and initial NI may be 2, maybe 3, maybe 4, and so on. And this gives you the series which we call it as a Lyman series. And this Lyman series, whose energy of the photon is in the range of UV energy. The photon which is emitted out in this Lyman series, when the electron jumps into the first level from any of the higher level, it gives the photon whose energy lies in the range of the ultraviolet radiation, or we call it as a UV radiation. So it is in the UV range. So it means this is in the UV range. Lyman series is in the UV range. Similarly, there may be chance that the electron may de-excite into n is equal to 2 from n is equal to 3. The electron may be de-excite from n is equal to 4 to n is equal to 2. N is equal to 5 to n is equal to 2. Now again this gives you the series, and this series is known as a Balmer series. So now in this Balmer series here, final level is equal to 2. The electron jumps into the final level which is equal to n is equal to 2, and the initial level which may be the higher level which may be n is equal to 3, which may be n is equal to 4, which may be n is equal to 5 and so on. So as a resultant, NF and I may be equal to 3, maybe 4, maybe 5 and so on. So as a resultant, this series is known as a Balmer series. And this Balmer series, whose wavelength of the photon is in the range of the visible light. This Balmer series gives the range is in the visible light. Similarly, again, the electron may be Similarly, the electron may be excited into n is equal to 3 level, n is equal to from 4 to 3, from 5 to 3 and so on. This gives you the Lyman-Balmer. This is the Paschen series. So in this Paschen series, we say that final level is equal to n is equal to 3 and initial level maybe 4, maybe 5, maybe 6. And this is known in the range of IR range. IR means infrared range. So this gives you the different wavelengths. It means this gives you, if the electron jumps into n is equal to 1 from any of the higher level, this gives you the series which we call it as a Lyman series, and this Lyman series whose photon energy lies in the range of the ultraviolet radiation. One thing. Second thing, the electron may be excited into n is equal to 2 level from any of the higher level. From any of the higher level, n is equal to 2. So final level is n is equal to 2, higher level maybe n is equal to 3, higher level maybe n is equal to 4, maybe any other higher level. So this gives the F series, and this series lies in the range of the visible light, and which we call this series is the Balmer series. And the third series is known as a Paschen series, in which the electron jumps into n is equal to 5, n is equal to 3, from n is equal to 4, from n is equal to 5, from n is equal to 6 and so on. So this gives the series which we call it as a Paschen series. Similarly, in the onward direction you may call it as a Paschen, then Fund series, bracket series, then Fund series and so on. So this is the little bit complete story of the Bohr's atomic model. Okay, what is the Bohr's atomic model? And this model is a semi-classical model. This is not a quantum mechanical model, because look here, Bohr says that the energy of the electron in the first orbit is minus 13.6 electron volts. And the radius of this first orbit, which we have seen that radius r1 is equal to 0.52 angstrom. This is the radius of the first orbit, which is equal to, I will write it like that, radius r1 is equal to 0.511, yeah, 52 angstrom. Angstrom means 10 to the power minus 10 meter. This is the radius of the Bohr's first orbit. So Bohr says that the radius is fixed. Bohr says that the energy is fixed. But quantum mechanics says that we cannot measure the momentum and position of an electron simultaneously. This quantum mechanics is based on the wave nature of the particle. This quantum mechanics is based on the uncertainty principle, because the uncertainty principle says that we cannot measure we cannot measure the position and momentum of an electron of a particle simultaneously with 100% accuracy. We cannot measure. If we measure the position, there will be uncertainty in the momentum. If we measure the momentum, there will be uncertainty in position. Similarly, the second principle, uncertainty principle, is that we cannot measure the energy, this energy, and the time of stay of electron in any excited state simultaneously with 100% accuracy. So according to these uncertainty principle, there is a uncertainties in the measurement of energy, there is a uncertainties in the measurement of the position. So according to the quantum mechanics, we cannot measure it. So therefore, this model, which is the Bohr's atomic model, is not a quantum mechanical model. This is known as a semi-classical model. According to now quantum mechanics, what does it mean? Quantum mechanics says that the electron is here. If electron is here, n is equal to 1, the state of the electron can be described by a wave function. It means the wave function is a function which describes the state of the particle. So now, if we use the quantum mechanics to describe the state of the particle and to find out okay, what is the probability of the measurement of the electron in the n is equal to first state. So in order to measure the probability of finding the electron in n is equal to 1, we must have the wave function. We must have the state function. If the state function is not given, we cannot measure the probability of finding the position or probability of finding the momentum. So quantum mechanics is totally based on the state function. If the state function is given, then we can find out, we can measure the other variables. If the wave function or state function is not given, we cannot measure. So this is not a quantum mechanical model. So according to quantum mechanics, we will discuss later on.